Okay, now we're going to look at a class of functions called simple functions, and we'll be using these in the development of Lebesgue integration. They play a really fundamental role. And we'll be approximating other functions with simple functions. That's the title of this section is Sequential Pointwise Limits and Simple Approximation. And what simple approximation means is we're approximating measurable functions with these simple functions. And the very first category of functions for which we'll define the Lebesgue integral are the simple functions. And we'll need to talk about various kinds of convergence as things develop. We're dealing now with sequences of functions and ways that a sequence of functions might converge. So the following ideas may be familiar to you, some of it from maybe even Calculus 2, and the rest of it from a senior level analysis class. So we're considering a sequence f sub n of functions with a common domain E, a function f on E, and a subset A of E. For this sequence, we have the following definitions. So we're taking some subset of E, call it set A, and we're looking for convergence of this sequence f sub n to that function f. In calculus, I think probably you exclusively deal with an idea of pointwise convergence of a function. The sequence f sub n converges to function f pointwise on set A, provided the limit as n approaches infinity of f sub n of x equals f of x for all x in A. So if we were to translate this into epsilons and in capital N's, the traditional symbols, we'd say, let x be an element of A. So you'd fix the x value. And then you'd simply deal with f sub n of x, the resulting sequence of numbers. Once I fix an input value x, this is a sequence of numbers, and that's a number. And we do our usual epsilon in definition for the limit of a sequence of numbers. So in that sense, this is a pointwise convergence. You start with picking a point x in this set and then dealing with an associated sequence of numbers, corresponding function values. A sequence is said to converge pointwise almost everywhere on set A, provided we get pointwise convergence on set A set minus B, where the measure of B is 0. So we're throwing out a set of measure 0, but still maintaining elsewhere pointwise convergence. So that's pointwise almost everywhere convergence of a sequence of functions. This is new to you, I suspect, because you haven't used the almost everywhere vocabulary before, but fairly straightforward on that. A sequence f sub n converges to f uniformly on set A, provided for each epsilon greater than 0, there's a capital N, a natural number, such that the absolute value of f minus f sub n is less than epsilon on set A, this holding for all indices n larger than capital N. This, I doubt you encountered in calculus, might be buried somewhere in the high numbered exercises or something, but it's unlikely you encountered this in calculus, possibly talking about Riemann integrals, but it's I suspect not a calculus topic, but certainly you'd see this in senior level analysis. And the uniformity is being expressed right here. When they make a claim about a property holding on a set, what they mean is it holds for all, in this case, for all x values in that set, f of x minus f sub n of x. So when a property is claimed to hold on a set, there's some implication about all elements of that set, all x values in that set, because we'll be dealing with sets of real numbers. So what they're saying is, a little more informally, and this is the way you would have been introduced to it in senior analysis, for all epsilon greater than 0, there's a capital N that works for all those epsilons throughout set A. That is, if the index lowercase n is sufficiently large, at least as big as capital N, then throughout set A, we get f of x minus f sub n of x to be less than epsilon for all x in set A. So you're used to probably seeing these uniform ideas, uniform convergence, uniform continuity addressed in terms of for all x in some set. They're stating it here as what's highlighted there. On set A means for all x values in set A. And it's easy enough to come up with examples of sequences of functions that converge pointwise but don't converge uniformly. Okay. For now, we're interested in pointwise limits of measurable functions. Notice if we have uniform convergence on a set, then we've got the pointwise convergence. It's a stronger condition than pointwise convergence. Uniform convergence we're prone to deal with more in terms of integrals of limits of sequences versus limits of sequences of integrals in the Riemann setting. So that's where you would have encountered this uniform convergence stuff. We're not going to make a big use of uniform convergence in the short term. We're going to be interested in Lebesgue integrals after all. But let's take a look at how pointwise sequences of measurable functions behave. And according to proposition 3.9, they behave nicely. Let f sub n be a sequence of measurable functions on set E that converges pointwise almost everywhere on set E to some function f. The claim is that limit function f is measurable. Okay. Let's go through a proof of that. All right, remember what measurable function means. Dealing with f of x being less than c is a measurable set. This must hold for all real numbers c. It was the first proposition we saw in the previous section. Okay, first off, we got almost everywhere pointwise convergence. Well, that means we can throw away a set E sub 0 of measure 0. And then we've got the pointwise convergence on E set minus E sub 0. Throw out that set of measure 0. But we saw in the previous section that a function's measurable if and only if its restriction to E set minus E sub 0 is measurable. Proposition 3.5, part 1, I suppose. So without loss of generality, we can assume we've got pointwise convergence throughout E. Either that or we can prove it on E set minus E sub 0 and then throw in this little observation about measurability. All right, so it's a claim about measurability, not anything about claims of values of functions or anything, just convergence to a measurable function. Well, if we're dealing with measurable functions, then we will start with C, a real number, and we want to show, so let's sneak a peek ahead. We want to show this set right here is measurable. The x values in the domain of the function such that f of x is less than c. We want to show that's a measurable set for all real numbers c. Okay, so that's where we're going. Remember, that was what we had in terms of the definition of measurable function in the previous section. Well, that or three other things equivalent to it. So we could show any of those three. We're going to show the less than c deal. All right, for a given x value in E, where we're assuming pointwise convergence, we've got then the limit as n approaches infinity of f sub n of x equal to f of x. So that's simply this setting. That's the pointwise convergent stuff, given x. So we've got f of x less than c if and only if the following occurs. Okay, we got to translate this from a conversation about function f into a conversation about the f sub j's in the sequence. We're trying to show measurability of f. We know measurability of the sequence functions. That was hypotheses. All right, so f of x less than c, if and only if there exist lowercase n and k, natural numbers for which f sub j of x is less than c minus 1 over n for all j greater than or equal to k. All right, let's dissect that. It's probably not immediately obvious. Here's what's going on. We're backing away from c by an amount think of it in terms of an epsilon amount, by an amount 1 over n. We're going to let that part that we've subtracted away, we're going to let that get arbitrarily small by letting n get arbitrarily large. We're requiring this to hold for all natural numbers n. Okay, then it holds for big natural numbers, and in some limiting sense, this will go to 0. Also, we're looking at a term in the sequence, an f sub j of x. Well, we need j to get large as well. So what they're saying then is this holds for all k, a natural number. In particular, k can be large. And we're taking j to be greater than or equal to k. Since k can be large and j is greater than or equal to k, the j's must be large. So they're just combining together two pieces of information. The convergence of this sequence, f sub j of x, to the value f of x, first off, that's making the j large, and the fact that f of x is less than c, f of j is close to f of x. If we'll back off from this c a little bit, we can eventually, the eventually is the lowercase n in this note, or sorry, the lowercase k in this notation, when the j's get larger than k. Eventually, we can make these functions this close to c. After all, f of x is less than c. All right, so we need to express the set related to f of x less than c to these sets of the form f sub j of x less than some real number. Okay, well, consider x and e such that f sub j of x is less than c minus 1 over n. We were just talking about those. Those are measurable sets. Agreed? F sub j is measurable. Being measurable means the set of x values where the function is less than a given real number is a measurable set. That's exactly what we've got. X values where this function is less than that real number. This function, f sub j, is measurable. We got a sequence of measurable functions. So this is a measurable set that holds for all n and j. The j was the index on the f's, the sequence terms, the sequence of functions. So it holds for all j. All of those functions in that sequence are measurable, and it holds for all n. And just as long as we get a real number here, we get a measurable set out of this. But we need to make this observation about n and j's given what we're going to do next. So first off, this is a measurable set because f sub j is a measurable function. If we were to intersect from j equals k to infinity, such sets, that would be measurable. Each of the sets is measurable, so this countable intersection is measurable, first off. Shouldn't be an objection to that. What we need to do now is link together the set of x values for which f of x is less than c to these kinds of sets. And the claim is we've got x values where f of x is less than c, equivalent to the union from k equals 1 to infinity and n equals 1 to infinity of the intersection from j equals k to infinity of these sets here. First off, that's a measurable set. These are measurable as we had just observed. So the countable intersection of them is measurable as we just observed. And now we're taking those kinds of things and taking unions of those, countable unions of those. So we've got countable unions of countable intersections of measurable sets. We're in a sigma algebra, the sigma algebra of Lebesgue measurable sets. So indeed, that thing there is measurable. And if this thing here is measurable, then function f is a measurable function. So big picture, we've written this set, f of x less than c, in terms of unions and intersections of sets related to the f sub j's being less than some constant. These are measurable. Countable intersections and unions, this thing is measurable, and function f is measurable. So that completes the proof, provided you buy the fact that the set of x values for which f of x is less than c really equals this thing. Well, think of it like this. What we're doing is we want to make j large, so the f sub j of x is close to the f of x. And we want to make n large, so what we're getting for this upper bound is close to c. Right, we've got f of x less than c, so we want these f sub j of x's to be less than c as well in a limit. So we need both the n's and the j's to be large to produce these x values. We're intersecting from j equals k to infinity, right? So we're intersecting, in a sense, the tail, intersecting over the tail of that sequence of functions. The indices start at k and run from there. And we're making k ultimately large. Here we're taking a union from k equals 1 to infinity and n equals 1 to infinity. It's a countable union of countable unions, really. But the k's get large. Well, if the k's get large, then the j's have to get large, and then we're looking far out that sequence of f sub j's. Also, we wanted the n's to get large. When n gets large, we get this close to c, and we've got n ranging from 1 to infinity. So indeed, this will get close to c. So we get arbitrarily close to c as n gets large. As j gets large, which happens when k gets large, we get these being far out in the sequence of given measurable functions. So combining those two, large indices on the j and large values of n, are producing the x values for which this holds. That's the hard part, is that set equality. The rest of it's just sigma algebra arguments and kind of standard epsilon limit type things. But that shows a pointwise limit of a sequence of measurable sets is measurable, useful, not the primary objective on this stuff though, but we'll deal a bunch with sequences of simple functions, it turns out. First, a characteristic function on a set A is defined as follows. The Greek letter chi is used, chi sub A of x, defined to be 1 if x is an A and 0 if x is not an A. So it's like an off or on switch. When you input a value from set A, you get out 1. When you input a value that ain't in set A, you get out 0. So characteristic functions, possibly you've encountered this before. And characteristic functions are really important stuff. But the main character of interest is simple functions. And simple functions are, in a sense, linear combinations of characteristic functions. So a real valued function phi, defined on a measurable set E, is simple if it's measurable and takes on only a finite number of values. If the distinct values that it takes on are C1 through C sub n, E sub k is the x values in the domain of the function where phi of x equals C sub k. So E sub k is a set on which the simple function phi takes on the value C sub k. We'll draw a picture. Then the canonical representation of phi is phi of x equals a sum from 1 to n of C sub k times a characteristic function on E sub k. So we've used characteristic functions to give particular representations of simple functions. Here's a picture to make some sense out of this. Okay, there's a rather elementary simple function. Side comment, you know, if I was going to integrate that function phi as drawn in this picture, that'd be real easy. We'd just get 3 rectangles, which reminds me of how Riemann sums start. That ain't a coincidence. But here's a simple function. Granted, it's a really easy simple function. It's actually called a step function in calculus, or maybe analysis. But this is a simple function because it only takes on 3 values. It's a measurable function. Easy enough to see measurability. It's continuous for one thing. All right, the obvious way to represent this is the canonical representation. If I want to write this as a linear combination of characteristic functions, I'd say, well, on the interval 0, 1, let's take the characteristic function and multiply it by 1. on the interval 0, 2. Let's take the characteristic function on, let's say that correctly, on the interval 1 to 2. Let's take the characteristic function on that interval, multiply it by 2. On the interval 2 to 3, let's take the characteristic function and multiply it by 3. So we get phi of x is 1 times the characteristic function on the interval 0, 1, 2 times the characteristic function on the interval 1 to 2, 3 times the characteristic function on the interval 2 to 3, with appropriate respect for the vertical line test, which I didn't entirely reflect in the little picture here. But that's the easiest way to write this thing as a linear combination of characteristic functions. And because these sets that we're dealing with, these sets are disjoint, then this is a characteristic, this is a canonical representation. The function takes on the value 1, and it does so on the set 0, 1. The function takes on the value 2, and it does so on the interval 1 to 2, and so forth. Here's another representation that ain't the canonical representation. Suppose we took the characteristic function on the interval 0 to 3 times 1 plus characteristic function on the interval from 1 to 2 times 1 plus a characteristic function on the interval from 2 to 3 times 2. Okay. If I choose a number between 0 and 1, we pick up a 1 here and zeros from these two, and we get out 0. If I pick a number between 1 and 2, we pick up a 1 here and a 1 here and a 0 here, and that gives us 2. If I pick a number between 2 and 3, we pick up a 1 here, a 0 here, and a 2 here to produce a 3. But this is not the canonical representation, because here's the value 1. Well, the function doesn't take on the value 1 specifically on the interval from 0 to 3. It's the interval 0 to 1 where it takes on the value 1. Here we're looking at the interval the interval from 1 to 2. We got a coefficient of 1. It doesn't take on the value 1 on the interval from 1 to 2. It takes on the value 2. And similarly from 2 to 3. Here's a characteristic function. Yeah, but it doesn't take on the value 2. It takes on the value 3. We produce the value 3 in this awkward way of adding together various parts, but not a canonical representation, because the sets down here, the 0, 3, 1, 2, 2, 3 intervals, they're not disjoint. They would have to be disjoint in a canonical representation. The reason for this, as explained here, we're going to define in the very first step of Lebesgue integration, we're going to define the integral of a simple function. And we need to do so in an unambiguous way. So we need a way unambiguously to describe a simple function. That way will be the canonical representation. We use the canonical representation, no problem. There's only one canonical representation. So if we define something like the integral of a simple function in terms of a representation as a sum of characteristic functions, then we better use one that's unambiguous. We can't define it in terms of simple functions if a simple function's got a whole bunch of different representations. There might be conditions under which I can use different representations. But in the beginning, we define, say, the Lebesgue integral of this particular simple function. We would do so in terms of a canonical representation to give it a well-defined meaning for the definition of Lebesgue integral. And what we'll get when we define integrals of simple functions is something like Lebesgue sums. I'll get like like rectangles, function values, which are constants for simple functions, times the measure of a base. Up here, what we would get would be just a regular old collection of 3 rectangles like Riemann would get. Yeah, well, here we're dealing actually with step functions. And we could define Riemann integration in terms of step functions you may have in your senior level analysis. But these simple functions will play the role of step functions. And these simple functions will introduce what I will call Lebesgue rectangles and Lebesgue sums. Perfectly fine vocabulary. It's not in the book, but to draw parallels between Lebesgue integration and Riemann integration, I'll throw that verbiage around. Okay. When dealing with other types of functions, some other types of functions at least, we'll define the Lebesgue integral by approximating it with simple functions. So we need some results concerning approximating measurable functions with simple functions. The simple approximation theorem says the following. Let's just go to the proof. Let f be measurable and real valued on set E. They say that to eliminate the possibility that it might be extended real valued. Assume f is bounded on E. That is, the absolute value of f is bounded by some real number m. That'll keep it away from infinity right there, for one thing. Then the claim is, for each epsilon greater than 0, there are simple functions, phi sub epsilon and psi sub epsilon, for which phi sub epsilon is less than or equal to f is less than or equal to psi sub epsilon, and 0 is less than psi sub epsilon minus phi sub epsilon is less than epsilon. Okay, let's analyze that a little bit, maybe go back to the notes and look at a picture. Oh, this is claimed to hold on E. Again, when they say on E, they mean for all x in E. So what they're saying is, see, this second part says the phi function is really close to the psi function. The psi function minus the phi function is less than epsilon. So these must be close together for all points x in E. The phi is less than or equal to f, and the psi is greater than or equal to f. So f is sandwiched between these two, and these two are close together. So let's take a look at a picture. Because this picture really illustrates how the proof is going to go. So we'll look at the picture and streamline a little bit of the logic maybe in the proof. Here in blue, we've got some measurable function f. What we're going to do is partition up, remember it was a bounded function, let's partition up the interval, say from y sub 0 to y sub 3. We'll use the symbols c and d as well in the proof. But we've got a function that's bounded, so go to below the lowest function value and above the greatest function value. So bracket it off and then partition up the y-axis. Could be the first time you've seen us approach an idea by partitioning up the y-axis. Might have come up in senior level analysis. It could be the first time. It won't be the last time, conceptually at least. So we're going to cut this interval into a bunch of pieces. We're going to make the little pieces less than epsilon. For the sake of a picture, let's make epsilon kind of big and just 3 pieces. So we're going to the lowest value of the function to the highest value of the function or something like that, and partitioning that interval into pieces of size less than epsilon. All right, we're going to look on this first interval, y sub 0 to y sub 1, and run over here and say, hey, between here and here, let's see, I guess I should point at x values. Between here and here, the blue function lies between this value and this value. The function takes on the values between y sub 0 and y sub 1, starting here, going over to here. Project that back. It's on this set E sub 1 of x values on which that occurs. Between here and here, the function takes on values between that, somewhere between here, here and here. Yes, it is here and here. I need to be more precise. Between, I've left a bit ambiguous. It'll be on points here. Here we've got it taking on values less than y2. If I go straight down, those should align. And greater than or equal to y1. So here we get values between y1 and y2, including y1 and excluding y2 is how we'll deal with it. So here's part of the x values for which the function gives out function values. It's these function values that are between y1 and y2. Same thing happens over here. So we'll project back and get another piece of e sub 2 over here. E sub 3 is the x values that produce y values between y sub 2 and y sub 3. We get a chunk of it over here and another chunk of it over there. Projecting back, here's this set e sub 3. So on E1, we get function values between here and here. On E2, we get function values between here and here. And on E3, we get function values between here and here, right? In this interval or that third interval is what we get when we input values from E1, E2, or E3 respectively. Now, we were creating a psi function that's less than. Okay, well, let's just go where the function takes on values between y0 and y1 and project down and take that constant function as a piece of phi sub e. On the next interval, a function takes on values between here and here. Well, let's project them down in red to get this. Same thing over here. On set E3, the function takes on these values. We'll project them down to this value, y sub 2, the lower value in that subinterval. And then in red, you've got yourself, in this picture, a step function. But more generally, I may not know what these sets E are, because these e sub i's are, because, I don't know much about the function. They may be measurable sets, for all I know, versus nice, clean little intervals like in the picture. But we've got a function constant on a first set, constant on a second set, and constant on a third set. Those sets are E1, E2, which comes in pieces, and E3, which comes in pieces in this picture. And sure enough, the red function is less than or equal to the blue function. Also, the way we did it, by taking these points to be close together within epsilon of each other, any particular point in red is within epsilon of a corresponding point in blue on the curve of the function f. In the psi function, we want bigger values. So instead of taking the lower value on set E1, we'll take the upper value. Remember, the function had values between y sub 0 and y sub 1? Fine. Let's define psi to be y sub 1 on that set E1. Let's define psi to be y2 on set e sub 2 and y3 on set e sub 3. Now, the green function's always bigger than the blue function, and particular function values are within epsilon of each other by the construction of that partition. All right, that's the plan. The psi function is less than or equal to function f. The to say it correctly, the phi function is less than or equal to. The psi function is greater than or equal to. And the psi and the phi are always within epsilon of each other. Right? I'm reading vertically here. These two pieces are in correspondence for given x values. This is behavior of the function on the set e sub 2 for the record. And the red line here and the green line here, they're within epsilon of each other. The red line here, I look correspondingly to this green segment up here. Yeah, these are within epsilon of each other. The width of these little subintervals is less than epsilon, is the plan. So that's the idea. Now let's go through the formal proof with that as background. It's not too complicated. So we'll let CD be an open interval that contains the domain of the function, the range of the function, f of e, where e is the domain of the function. That can be done because you were told it's a bounded function. As we did, we bracketed on the top and the bottom by c and d, and then partition up this interval c to d into y sub 0, y sub 1, up through y sub n, and do so such that y sub k minus y sub k minus 1 is less than epsilon. That's when we chose the little consecutive y values to be within epsilon of each other. So think close together, though it didn't look like that in the picture because I was trying to draw something you could see. So we're choosing the y sub k minus 1, y sub k to be within epsilon of each other. Define I sub k to be the resulting intervals. So these are little intervals we'd have along the y-axis. Notice we've included the left endpoint and excluded the right-hand endpoint. In the conversation we just had, I kept saying between, and between is a bit ambiguous. Here's specifically what we mean. We need to make sure we keep those intervals disjoint because we're going to produce a canonical representation of a function. And define E sub k to be the inverse image of I sub k. So this is when we went back to the x-axis and picked off set E1. Set E2 came in pieces, and so did set E3 in the picture. But we're taking inverse images of these outputs. So it's when the function lies in the band from y sub k minus 1 to y sub k, including the left endpoint and excluding the right-hand endpoint in that band. So we're projecting back, taking inverse images, nothing to do with inverse functions, inverse images here. Since f is measurable, then each of these E sub k's is measurable. We're dealing with a function, an inverse image of an interval. This interval is of this form. So we'd be looking for function values that are greater than or equal to y sub k minus 1 and strictly less than y sub k. That we can write as an intersection of two sets in the definition of measurable. The x values such that f of x is greater than or equal to y sub k minus 1. Well, that's a measurable set if f is a measurable function. Intersect the x values in E such that f of x is strictly less than, because of the open part, strictly less than y sub k. Well, like in the previous proof, that's a measurable set too if f is a measurable function. Definition of measurable function. So we get these E sub k's to be measurable. Always got to throw this word measurable around. I guess some of this could be accomplished with non-measurable functions, but we got no need for non-measurable functions, no use for them. And we even define simple functions to be measurable in the definition. We've got measurability of the E sub k's. So what we'll do is what we did in a picture. Define phi sub epsilon to be a sum from 1 to n, y sub k minus 1, characteristic function on E sub k. Y sub k minus 1, that's when you kind of project it downward. And define psi sub k to be y sub k. That's where we sort of project it upward. Characteristic function on those E sub k's and summing. All right, well, both of these are simple functions. They take on a finite number of values. They take on these values in this little list here. And this is a canonical representation because of the way we chose the E sub k's. We looked at this disjoint stuff here. We took inverse images. We get disjointness of the E sub k's. These are canonical representations, in fact, for two simple functions. All right. Does it satisfy the conditions it needs to be? We got simple functions. By the very way we created them, we've got this satisfied. We need to see if they're close together. They will be. We saw that in the picture. For x, in the domain of function f of x is in I sub k for some k. We partitioned up the range of the function. So phi sub epsilon of x equals some y sub k minus 1, the one that determines this interval, I sub k. That's less than or equal to f of x, chosen this closed interval. F of x in this interval is strictly less than the right-hand endpoint, the y sub k, and the y sub k is a psi value. So we've got f of x sandwiched between those two as claimed. We could replace this with a strict inequality from the construction. We see that. Also, y sub k minus 1 was less than epsilon. We chose the y values to be within epsilon of each other. We did so right there. So that means the psi and the phi will have to be within epsilon of each other. We get the inequality psi sub epsilon of x minus phi sub epsilon of x is less than y sub k minus 1. That's using, let's see, comparing the y sub k to the psi sub epsilon and comparing the phi sub epsilon to the y sub k. So that produces this inequality. And that's the second part, and then some. We know this to be less than epsilon, so there you go. So we can approximate measurable functions as accurately as you'd like, pointwise, with simple functions. That'll be useful because in the beginning of Lebesgue integration, there will be simple functions. And then based on simple functions, we'll integrate other kinds of functions. But it all starts with simple functions, and the other kinds of functions will be approximated with simple functions. And that's how we'll go through and define the integral, the Lebesgue integral of bigger classes of functions. Content of chapter 4. Next result gives a condition equivalent to the measurability of a function, but this time in terms of approximations and its relationship to a sequence of simple functions. Claim is an extended real-valued function f on a measurable set E is measurable if and only if there's a sequence phi sub n of simple functions on E which converges pointwise on E to f and has the property that the absolute value of phi sub n is less than or equal to the absolute value of f on that set E for all n. In addition, if f is non-negative, we can choose the phi sub n sequence to be an increasing sequence. I like monotone sequences. I know a little bit more about monotone sequences than I know about other sequences, and that's what they're doing with this increasing idea. First off, extended real valued function A. Okay, so they're allowing it to take on extended real numbers. They're allowing the symbol infinity to be a function value with the obvious interpretation in terms of inequalities, and they're making some inequality statement over here. And it's if and only if. All right, first, suppose a sequence phi sub n of simple functions on E exists as described. So we've got a sequence of simple functions, it's an if and only if result that converges to extended real valued function f. Well, you know simple functions are measurable. The definition of a simple function was that it's measurable. And we saw earlier that the pointwise limit of a sequence of measurable functions is measurable. So if we've got f as a pointwise limit of this sequence of simple functions, they're all measurable, then f is measurable. That's what proposition 3.9 says, and that ain't the hard part. So if we can approximate f, or if we can write f as a limit of simple functions, then f must be measurable. So now we need to do it the other way around. We need to say, suppose f is measurable, we need to approximate f with simple functions. We need to create a sequence of simple functions, and we'll do it by approximation because we already know we can approximate measurable functions by simple functions. That's what we did in the simple approximation lemma. All right, first, got a little deal here about some absolute values. We'll assume that f is non-negative on set E. If we can prove that, then we can prove the general case by expressing f as a difference of two non-negative measurable functions. Details are given in problem 3.23. So we're going to assume f is non-negative, so we can at least drop those absolute values. In the event that it could be positive or negative, it will follow from this result. That details to be given in that exercise. Okay, well, let n be a natural number. That'll be an index on one of these phi sub n's. Define E sub n to be the x values in E such that f of x is less than or equal to n. Okay. We're going to define a simple function, and it's going to be bounded. We knew some things about bounded functions. The simple approximation lemma required boundedness of functions, so we're about to do something related to boundedness. But E sub n is the x values where the function is less than or equal to n. That's a measurable set. If f is a measurable function, definition of measurable function, these kinds of x values are measurable sets. Less than or equal to, greater than or equal to some real number, or any real number. We choose the real number n, where it's natural is given. The E sub n's are measurable. The restriction of f to this measurable set is a non-negative bounded measurable function. It's non-negative because we're considering that without loss of generality. It's bounded. Yeah, it's bounded below by 0, by the non-negative part, and above by this parameter n. F on E sub n is bounded. F restricted to this set is measurable. We showed, I guess it was proposition 3.5 part 2, the restriction of a measurable function to a measurable subset of its domain is also a measurable function. Restrictions of measurable functions to measurable sets are measurable themselves. So f restricted to E sub n, non-negative bounded measurable function. All right, bounded, we can apply the simple excuse me, the simple approximation lemma to bounded functions. By the simple approximation lemma applied to the restriction of f to E sub n, we needed f to be measurable and bounded. Check. On E sub n, f behaves like that. Okay. Well, then with epsilon equals to 1 over n, we know there's a simple function. Let's call it phi sub n. Oh, and a simple function psi sub n, defined on E sub n, satisfying the conclusions of that previous section. Our previous result, we've chosen epsilon to be 1 over n. Other than that, this is exactly what we had in the simple approximation lemma. So we've got, let's see, bounded below by 0. Right, we knew we were dealing with a non-negative function. We'll get each of those simple functions also bounded below by 0. The problem is all this happens on E sub n. And we've got a function f defined on a bigger set E. So we're going to extend each of these phi sub n's to all of E by setting phi sub n of x equal to n if f of x is greater than or equal to n. So here's what we've done. We've approximated function f with these simple functions phi sub n, but we had to cap it. So I think of it like cutting the grass. A lawnmower comes along and cuts off the top of that f function whenever it's greater than or equal to n. So chops that top part of that function off, and we're capping these simple functions to be that constant of the upper bound, the level of the grass, as it were. All right, that's just another value, another single value added to the phi sub n. So when we take phi sub n and extend it to all of set E, by doing this, we may not be, for particular n values, very close to f of x, because f of x could be a lot bigger than n, and phi sub n of x is equal to n. For particular n values, these could be far apart. We'll deal with a convergence in a second. But the phi sub n's are now defined on all of E, and they're still simple functions. We added one function value, the function value n, to the phi sub n's. The extended phi sub n simple function is defined on E, still satisfies these conditions. Before we extended it, it satisfied those conditions. We've just defined it to be n, where f of x is greater than or equal to n. So for such x values, of course, we still have this kind of behavior. So we can say this inequality holds on all of set E. We claim that the sequence phi sub n converges to f pointwise on set E. All right, so we've created a sequence. We created this sequence of phi sub n's. Now we need to show the pointwise convergence. Well, if f of x is finite, remember, we're dealing with an extended real valued function. That means at any x value, we're either getting out a number or we're getting out the symbol infinity, which I interpret as a limit. Limit as x approaches infinity of x. I interpret infinity still as limits, just as in calculus 1. So suppose f of x is finite. Choose a capital N for which f of x is less than capital N. Okay, as n increases, remember how we cut off that function phi sub n at level n? Well, level n plus 1, you've cut it off 1 unit higher. N plus 2, you've cut it off 2 levels higher, and so forth. That's how we cap these. We kept them finite, but when n gets large, we're allowing these phi functions to take on big values. Eventually, that is for some capital N, we'll have f of x less than that capital N, in which case we'll have f of x minus phi sub n of x less than 1 over n for those x values. So eventually, what you'll see is the function values will get bigger and bigger and bigger until they match the value of function f, in which case we'll get them will match. They'll be close to the function, but the phi values as n increases will keep growing until n passes f of x. Then we'll treat them like the usual values that we had in earlier stages. We've got the f of x minus the phi sub n of x less than epsilon. Well, 1 over n, as we've chosen it to be. So if f of x is finite, eventually we get this kind of behavior. N goes to infinity, this goes to 0, so the limit as n approaches infinity of phi sub n of x equals f of x. When the function's finite, no problem. What if the function's infinite? Well, then phi sub n of x is going to equal n, no matter how big n is. For all natural numbers n, if you've got, you might think in terms of a vertical asymptote. What we're doing is we're going up, capping, and coming back down in a simple way. Well, as n gets bigger, you see these little phi sub n's keep moving up near that vertical asymptote. Of course, we're dealing potentially with functions way more complicated than that, but you might think of it in something like that manner. Phi sub n of x equals n for all n. Well, n can get large, so the phi sub n of x will have a limit of infinity. That is, the limit as n approaches infinity of phi sub n of x. Well, phi sub n of x is always n for those x values. The limit as n approaches infinity of n, that's infinity. And that equals the f of x value. We're dealing with functions that can assume the value infinity. Nothing more than that. We're not dividing by 0 or anything bizarre like that. We're just dealing with functions that can take on the value infinity, and that has meaning as a limit, has meanings in terms of limits. So we've got the limit of the phi sub n's to equal f of x when f of x is infinite and when f of x is finite. So we do have pointwise convergence. Okay, let's see. We haven't dealt with the increasing part. So we've dealt with the phi sub n's were chosen in such a way that they were less than or equal to f. In the case that we had everything positive, the negative has not been dealt with. That's left for that one exercise. And we still need to deal with a non-negative case. We may choose the phi sub n's to be increasing. Okay, we're going to do that in a really easy way. There's more complicated ways of dealing with it. We'll choose to maybe replace the phi sub n's with a phi sub n prime or something. I wouldn't mind a different symbol for this. This is how the book approaches it. But we could define a new sequence by replacing the phi sub n function with a maximum of phi sub 1 through phi sub n pointwise. Then when you add more stuff, the maximum won't get smaller. I want to think, well, now I add a phi sub n plus 1. In some places, I may get bigger function values. Yeah, well, bigger than or equal to. And that's what increasing means, right? Not necessarily strictly increasing. So we'll create a sequence of the maximums. Hey, the maxima of a collection of measurable functions is measurable by theorem 3.19. It's simple as well. These take on finite values, each of them, so the max will take on finite values as well. And so the new sequence is increasing. That is, at any particular point, as n iterates, that function value either stays the same or gets bigger. That's what I mean by an increasing sequence of functions. Let's see, a pointwise subsequence of the original sequence. It converges to f pointwise as well. So we're still getting the pointwise convergence. I got to shift to a subsequence of the given sequence. The given sequence converge, the subsequence will converge as well to the same value. So we can approximate measurable functions with simple functions. We needed boundedness that first go round in the simple approximation lemma. In the simple approximation theorem, we can get a sequence of simple functions that converges pointwise to any extended real valued function f that's measurable. So we can approximate measurable functions with simple functions. That will be most useful when defining Lebesgue integrals. And that completes that section. We're going to step aside a little bit in section 3.3 and look at some behaviors of sets of real numbers. And we'll introduce the word nearly in a little more detail. It's popped up in the past. And that'll take care of the chapter 3 material. And then in chapter 4, we'll get down and start doing the Lebesgue integration. So have a nice day. I'll see you soon in section 3.3.